Okay, so we're recording. Last time we just barely finished chapter 1, so we're moving on now to start with chapter 2. First thing we have to do is a couple of kind of formalities and definitions, and we just have to kind of set some groundwork. So apologies, this is going to be a little bit boring for a couple of, well, anyway, for a few minutes. So we're going to start off with the definition of what is a function. This is very commonly misunderstood and importantly misunderstood. A lot of people think a function's a formula. That's just not good enough in a situation like what we're in now. So specifically, what a function is a trio. It's a list of three things together, all of which make up what a function is. So specifically, a function has a domain. That's part of the definition of what a function is. And that's just, where do the inputs that this function is going to be defined on, where do those inputs come from? Secondly, a target. Now, sometimes people like to call it the codomain. To me, that seems unnecessarily stuffy. I think target communicates the idea, because that's where the outputs from the function go to, right? Just like if you were shooting at a target, right? So it seems like a reasonable choice. Last part of the trio is the rule of assignment. This is what a lot of people think of as being the formula, which again, a lot of people think of as what is the function itself, but again, it's not. It's one of the three elements of the trio. So the rule of assignment, sometimes called the formula, just tells you exactly what is the output for any given input. It doesn't have to be a bunch of algebra. It just doesn't. Okay, so these three things. So here's some functions. Just to get notation set up, this is the kind of notation that I'm going to be using a lot. It's very standard. The idea is that whatever your domain is, you put that there. Whatever your target is, you put that there. And notice this arrow here is suggesting what the function does. The function takes points, values, from the domain and produces outputs that are in the target. And so you can kind of think of it as like there's an action where stuff is going from the domain to the target. All right. So the rule of assignment is the thing that actually does the from here to there. And typically, whatever the name of the function is, we'll write the name like that. And of course, y'all know natural log, and the exact formula for how to write that down is something y'all have seen in other contexts. Okay. All right. Now, just for contrast purposes, here are three different functions. F, G, and H, all of which, just because I can, all of which are using the same rule of assignment. So the rule of assignment for all three of these functions is, given a student, what is that student's ID number? And notice, there's no algebra in this rule of assignment. It's not really a formula. Right? Okay, so a lot of people would say, again, that, all right, well, if F, G, and H are all computed by the same rule of assignment, then they're all the same function. But they're very importantly not, because a function is much more than just the rule of assignment. It is the trio. So, for example, F is a domain, a target, and the rule of assignment. G is domain, target, rule of assignment. And notice these are different functions because they have, in this case, different targets. F and G are not the same function. They're not the same trio because they differ in one of the elements of the trio. Okay. Everybody on board? Okay. All right. Okay, a little bit more lingo. This is a little annoying. You got things you have to get said. I want to define something called the image of a function. The image of a function is the set of actual output values that come out of the function. Now, a lot of people conflate this with target, and it's importantly different. as per the following example. Here is a function. Notice domain, target, rule of assignment. In this case, actually a formula. That's nice. The target, as previously discussed, the target is this. This is the world that I am requiring that all of the outputs from this formula have to land in, and thankfully they do. Whatever real number from the domain I plug into this formula, what will come out will always be a real number, right? So, cool. That's the target. The image, again, the image is the set of actual outputs. And if you think about what numbers actually come out of this function, and again, I remind you, only real numbers are allowed to go in because that's what I've set up as my domain. When you square any real number, only non-negative values will ever come out. Right? So the image is just the non-negative numbers. And so notice there is a significant difference. There we go. Okay, significant difference then between the target and the image. The target, I almost arbitrarily chose to be the unnecessarily large set of all real numbers. The image, I don't get to choose. The image is what it is. It's whatever the actual set of outputs actually is, in this case, the non-negative real numbers. Okay. Everybody good with that? Yeah. Mm-hmm.
Is there a rule of assignment that affects the
Yep. Mm-hmm. That's right. Okay, so related lingo. Again, these things just have to get said. When you have a function, and if you're talking about the whole function, the image is the set of all of the actual outputs. But if, for a given function, if you're interested in the image of just a single input value, the word image means something very much more sort of specific. For a given input, the image just means what is the corresponding output. Right. So if I talk about the image of x, well, x is a single input. The image is the corresponding single output. Everybody okay? Okay, the next term, very closely related, it kind of goes backwards. Suppose you have a given output value. Let's suppose I look at some output value y. If x is an input that gives rise to that output, then we say that that x is a pre-image of y. So the idea is that it's the thing that came before the y, and so that's the term pre-image. Everybody okay with that terminology? Same kind of natural? Yeah.
Does that make pre-image equivalent to input?
Yeah, kind of. I mean, it is an input, but it's specifically the input that gives rise to a specified output. Yeah. Does that make sense? Yeah. Okay. All right. So who cares about that? Why do we need this terminology? Well, we need that so we can define this. There's a bunch of words here that turn out to be important. You'll see why they're important in a few minutes. These words, all of them, you'll notice, are defined by looking at a point in the target. In fact, looking at all of the points in the target and looking at their corresponding pre-images and counting how many there are. Right? And so, for example, some functions, not all, but some functions have the feature that every point in the target has at least one pre-image. At least one. Some functions have this characteristic. So here's one of these functions. This function right here has that feature. Let's take these one at a time. We'll look at the whole target. We've got to look at all the points in the target. Right? So looking at that output point here, how many pre-images, how many points lead to this output value? Well, just the one. But one is at least one. So, cool. So far, so good. All right, next one. What about this point? That point has two distinct preimages. Right? This green point goes to my specified output. This green point also goes to my specified point in target. Okay, so this point here has two, which again, still at least one. Right? And you can go on down the list. And at a glance, you can see that every one of these points has indeed at least one preimage. And so this function is what we call an onto function, because you might say that the output values sort of lay entirely onto the target. It fills up the entire target. It covers the entire, something along those lines. Everybody okay? Also, common terminology to be aware of, surjective. So, something to remember. Okay, now let's look at this function right here. This function is not onto, because not every point in the target has at least one preimage. Most of them do, but not every one. This point right here has 0 preimages. Nothing lands on that output, on that hopeful, on that candidate output, right? This point on the target, nothing lands on it. It has 0 preimages. 0 is not at least one. This function is not surjective. Everybody see what I'm doing here? Right? Okay. Okay. On the other hand, this point is something else. This function is something else. This point, I keep saying point. This function does satisfy the one-to-one, aka injective requirement. That is, every one of these outputs has at most one preimage. That has 1, that is at most 1. That has 1, that's at most 1. That has 1, that's at most 1. This has 0, which is at most 1. And so, condition satisfied, this function is injective. Everybody see what I'm talking about? Some functions are neither. Actually, depending on how you count, most functions, in most cases, are neither. This point isn't injective, or this point has too many preimages to make the function injective. This point, that point has too few preimages to make it surjective. So it's just neither. Too bad. And this one is both, because every point in its target has exactly one preimage. So this is what we call a bijective function, sometimes called invertible. And that's why we actually care about this whole business about preimages and images and surjective, injective, because invertibility is important. And we're going to need to be able to talk about inverse functions. Y'all have already, probably, by the way, talked about inverse functions in your single variable calculus classes. You've talked about arc sine, right? You've talked about how to use the knowledge of the derivative of x squared to compute the derivative of the square root, right? There's some little clever algebraic moves that you can do there that require understanding a function to be invertible. And it could be that invertibility still was never actually defined, and that's a little sloppiness that we need to solidify. Okay. All right. So why do we call such a function invertible? Well, because if I were going to invert this function, if I wanted to be able to go sort of the other way from right to left instead of left to right, and if I wanted that to be a function, I would need to know for every point over here in what was the target, which will now be my domain for my new inverse function, I need to know that there is exactly one previously known as a preimage of the original function, exactly one now image of the inverse function, right, that this goes to. And you can only get that there is exactly one image of the inverse function if there was exactly one preimage of the original function. So this is exactly what we need. All right, so applying this to functions y'all have seen before. Let's see here. Let me actually do this. Here we go. A couple of functions y'all have seen before. Here is the squaring function. Right? Yawn. Boring. Right? Real numbers in, real numbers out. I mean, right? Who cares? Whatever. We're just squaring numbers. Nothing deep. Right? And yet here's the problem. That function as written, not invertible. If I were to say, let's invert that function, I am therefore responsible for taking every real number, what had been my target, now going to be my domain if I'm going backwards. I would need to know for every real number that I can find exactly one square root. I don't know what I did there. I think I bumped into something. And that's just not true. 25 has too many square roots. That's 2 of them. Negative 48 has too few square roots. It doesn't have any among the real numbers. Right? So the function is just not invertible. So if you want to talk about the square root as being the inverse of a function, you've got to fix the problem. The problem is that this was a bad choice at domain. This was a bad choice at target. And I can fix it, though, very easily by writing this down. This function is happily invertible because for every non-negative real number, indeed there is exactly one non-negative square root. Perfectly fine indeed. Okay, so that's an invertible function, and the inverse, known as the square root function, is therefore perfectly definable. Everybody happy? Questions? Okay. All right. They'll fix the AC in this building eventually, I guess. Okay, sine, another example. Now, it's tempting to just look at the formula. Who cares about inputs and outputs, whatever. Real numbers in, real numbers out, who cares? Well, if you're not careful, if you look at all allowable real numbers in and all real numbers allowed to be out, sine is not invertible. There's too many angles whose sine all give the same value. Right? So again, easily fixed. We fix this by saying, well, we're going to define what I call the invertible sine function only for a restricted collection of angles. We're going to set the target carefully, strategically, to allow only these actual achievable outputs. And having done that, this trio, again, it's very important that it's a trio. Right? This trio is perfectly invertible because, as you can see from this picture here, looking at this curve, the graph of that function, for every blue there is exactly one green, and vice versa. Everybody good? Okay. Don't forget, by the way, about the unit circle. Ultimately, if you're not going to use the specific advantages that graphs offer, I think there's a case to be made that it's really ultimately simpler to think about sine from this point of view. Sine and arc sine, depending on which way you're going, is just a relationship between angles on the unit circle and their corresponding y-coordinates. Right? So sine and arc sine both can be thought of as, well, just whichever way you're going between green angles and blue y-coordinates. Very simple, ultimately, point of view about sine and arc sine. Okay, moving along. Bunch of boring lingo. I'm going to be super quick with this because this is very readable and it's just terminology. We need to be able to talk about whether a function has multiple inputs allowed or perhaps just a single input allowed. And we distinguish these cases by these two terms, single variable, multivariable. I hope that makes sense, right? Input variables, you either have one or you have more than one. We also need to distinguish functions by how many output coordinates are there. And again, there might be several. or there might be just the one. And so we use these terms. If there's only one output, then it is a real valued function because what comes out is a real value. Right? Or if there's several outputs that come out, that makes up a vector, and thus we call it a vector valued function. Okay, so it's just terminology, but it's got to get said. A bit about component functions. Y'all can read that. That's pretty readable. I like to observe at this point that this sounds like a really complicated idea right here, a vector-valued multivariable function. It's pretty scary, right, just to hear as a term. But it's really not that big a deal. It's not a rare thing to come up. In fact, in idle chit-chat and talking about the weather, right, completely trite and trivial conversation, you are talking about a vector-valued multivariable function because, well, it's multivariable because there's various contributors to talking about weather. If you're going to talk about the weather, well, where? Longitude, latitude. Are you in an airplane at 30,000 feet or are you on the ground at 300 feet? I think we are. By the way, are we talking about weather now or are we talking about the weather last week? Right? So 4 different variables, just so we can know what weather we're talking about. And then once that's all clarified, what is the weather? Well, the weather consists of a bunch of things. I mean, high pressure, low pressure, wind speed, humidity, temperature. There's a bunch of things to talk about. They're all part of the weather. So again, idle chit-chat very often is a discussion of a multivariable function. So something to keep in mind. This is not niche, rare stuff. This is what the world is made up out of. Okay, so how to visualize functions. This topic doesn't really come up very much in single variable calculus because if there's only one input variable and only one output variable, we draw the graph. It tells us everything we need. We never can't draw it. It's just always there, always convenient. In single variable calculus, pretty much every picture you ever see is pretty much a graph, very rare exceptions. So you can afford to be sloppy on what a graph is precisely if in fact that's the only thing you're ever going to do, and so you don't need to be careful. You kind of get accustomed to, well, this is how you kind of interpret things and this is kind of how you handle things. That's not going to be the case in this class. We're going to need to talk about several different kinds of constructions to help us understand functions from a geometric point of view. And so we're going to have to be very precise and clear on exactly what these are and how they're different. So let me start real quick with an example, and I'll go back to what we were just to the definition that I just sort of skipped. Here's the familiar case. Y'all have seen a million examples of real valued single variable functions, right? Calc 1 functions. And what we do if we want to talk about such a function, the graph is this curve. Let me do better than that. The graph is this curve consisting of a bunch of points where the first coordinate of the point is what you put in to the function. Just for the clean it up. And then the second coordinate is what comes out of the function. Right? So first coordinate's the input, second coordinate's the output. Old news, y'all have done this a million times, right? Everybody happy with that? Look familiar? So there is, of course, only one input because the domain is R1. There is, of course, only one output because the target is also R1. Okay, so when you have a single variable graph, you're going to get a bunch of points that make up a curve, typically. Okay. All right, so what we're going to do is generalize based on that. So I'm going to do the morally equivalent same thing here. And if you have multiple input coordinates, those multiple input coordinates you list first, just like we did in the single variable case, input first. If you have multiple outputs, namely a vector valued function has multiple outputs, then those multiple outputs go next. And altogether, the graph is the set of all such ordered n plus m tuples, I guess you could say. Right? It's kind of a weird thing when you write it down like that, but this is just kind of the copycat of our single variable notion that y'all already know. Everybody see the analogy? See how this is a natural sort of analogous thing? Okay. All right, I'm going to show you another example, a higher dimensional example momentarily. I do want to real quick, though, talk about a different way of thinking about it that is very useful. So back to the first single variable real valued case. When you have a function to form the graph, if you just look at the values of the function, and if you set the output values equal to a new variable, that equation that results. You take the values of the function and set it equal to a new variable, that resulting equation is the equation of the graph. Right? And again, y'all have seen this a million times. You write down that equation, you draw this picture. Cool. So it's just a different way of thinking. It's nothing different from what we already said, just a different point of view, yeah.
What does the D refer to, the definition?
Yeah, well, so sometimes when you say I've got n input variables, if I write Rn, that would require that every n tuple be in my domain. In other words, that my formula has to actually be computable for all those n tuples. So this business about D, this is just me recognizing that, my formula has a square root in it. Sometimes I'm not going to be able to compute that because the thing under the radical is negative. So I can only define my function on some subset, perhaps, of Rn. And I'm just giving myself that flexibility. That's all. Yeah. Okay. All right. So, here we go. Two-dimensional example. Keeping in mind the single variable example that we're all very familiar with. Here's the two-dimensional version of that. Notice now two input variables. My domain is R2. That means, again, two input variables that go first in the little tuple that I'm creating there. Right? One output value goes next, and the graph is the collection of all points of that sort, and so all points that look like that. Everybody good? Alternatively, if you prefer, the other option for how to think about this, we take our formula. That's our formula. We set our output values equal to a new variable. Notice that the function f was defined in terms of both x and y. X and y are inputs. I can't have the output value called y. Y is already being used as an input. Right? So I have to bump up through the alphabet, call the output Z. It doesn't matter what you pick. I mean, alphabetically convenient is common, but it doesn't matter. Okay. So another way to say it is that the graph is the surface for which that's the equation. Okay. Take your pick. Now, here's another way to think about it, by the way, and this is a reasonable point of view. It's a little sloppy, but it's satisfying and somewhat instructive, even if it's a little bit technically not quite legal. Our domain is R2. Our domain is all values of x and y. You might say our domain is the xy plane, and check it out. I feel like I can see the xy plane right here as sort of the sort of part of the space that this graph is being drawn in. Okay, so technically it's a little bit bogus. R2 is a collection of points with 2 coordinates only. R2 means 2 coordinates. Technically, the xy plane in space is x comma y comma 0. This is a bunch of points with 3 coordinates. It's just one of them happens to be 0. So, you know what I mean. Let's go ahead and sweep that formality under the rug. It's nothing to worry about. So, you can think of a function as taking a point in the domain, like so, and the formula for the function tells you how much to push up to get to a point on the graph. Right, so this is a nice way to think about it. The function is just telling you how much to push up from the xy plane. And now I'm going to make a hand-wavy appeal. The plane, the domain, is clearly two-dimensional. So the appeal, if I have a two-dimensional thing, and if every point in this two-dimensional thing gets pushed up, perhaps by different amounts, right? Asymmetrically, every point in the two-dimensional plane gets pushed up, I claim that that means you're going to get a two-dimensional surface as your result. Right? You start with a two-dimensional thing, points just kind of rise by different amounts. The result is also a two-dimensional thing, and thus a surface. So, good general rule of thumb, when you have a function and you draw the graph, the dimension of the graph and the dimension of the domain, those dimensions will always be equal. Surface is an intrinsically two-dimensional thing. Make sure not to conflate the dimension of the surface itself with the dimension of the world that it lives inside of. Right? A surface is two-dimensional. Surfaces have area. Surfaces don't have volume. It's an intrinsically two-dimensional thing. It lives in a three-dimensional space. All right. Okay. So, single variable. Here's our first multivariable example. And here's the bad news. That's our first and last multivariable graph that we can draw. Because let's see what happens if we try to jack it up just one extra measly dimension. Right? Let's look at this example here. If I have a function of 3 input variables. Okay, so 3 inputs go first. There's only one output. Okay, fine. That output goes next. The graph consists of a bunch of points that look like this. Those are points in 4 dimensions. I cannot draw that or visualize that. Game over, we lose. That make sense? So it's a kind of a disappointment. Graphs, again, they're our best friends when we're in single variable calculus. They're the kind of the perfect tool for visualizing single variable functions. Not only can we always draw this picture, we never run out of dimensions, but there are a lot of very handy relationships between the algebra and the geometry. The algebra of this function, derivative, second derivative, stuff like that, is evident in the geometry of the graph. The slope being positive or negative, right? The concavity being negative or positive, up, down or up, right? It's all geometrically visible on the graph, telling us algebraic information about the function. That's awesome. Gotta love it. That's why they use graphs so much in single variable calculus, because graphs are super when you can draw them, when they're accessible to us, and they just usually aren't. Okay, so that's a huge disappointment. The way we fix this disappointment is we come up with other tools, namely other constructions that are not graphs, that have different relationships to the original function, for which the calculus will look different. It's just a totally different sort of world. to have to make sense out of. And so all of a sudden it becomes really important not to conflate the graph of a function with the function itself. We're going to need to be able to think about far more than just graph pictures and graph calculus. We're going to have to understand other kinds of pictures. What does calculus look like in these other kinds of pictures? It's totally different. So this is so we have to be careful with our language. We have to be careful with our interpretations, and make sure to take the language really, really seriously here. And one that I've written down here to warn you about is, again, a lot of students will point to a graph and say, "Hey, let's look at this function." Well, you're conflating a function and a graph. You can't do that anymore. Another thing is, a lot of students will use the word graph whenever they see a picture. You can't do that anymore. Not every picture is a graph. So again, be careful with that. Okay. All right, moving along. Let's see here. This next one is what I like to call the literal picture. This is just my preferred terminology. I think I may have made that up. Keep in mind that if you have a function, there is a wrong color. There is a domain. Check it out. I drew a picture of the domain, R3. There it is. There's a target. Okay, cool. R1 there. I just drew a picture of the target. What does the function do? The function takes points out of the domain and puts them in to the target. Again, suggesting some sort of a movement from left to right. And so that's what I'm drawing here. Notice this is really just a literal picture of what is being suggested by this notation. And this turns out to actually be really, really handy. Now, I want to confess right off the bat, this looks pretty disappointing. Where's the shape? Right? You look back at these pictures, the shape, the curve here in this case, tells us stuff. Slope and concavity give me algebraic information. That's awesome. This shape is really useful. There's no shape to look at here. So what gives, and why would I ever want to use this clearly, seemingly disappointing thing, right? And let me address my own complaint here. That is an apples and oranges complaint. This is a really hard function to represent, right? Functions with 3 variables, really hard to represent. Functions with 1 or 2 variables, much easier to represent. That wasn't a fair comparison. If I want to compare fairly, this picture of a function of 3 variables, the fair comparison is what did the graph give me in that situation. And the graph gave me nothing. Right? Crash and burn. Complete loss. Right? There's nothing there. So the actual comparison here in this context is, which do you like better? No picture at all, or a disappointing picture? And I'm afraid you're going to have to pick the disappointing picture as being better than nothing at all. Everybody happy? Now that said, there are some nice things that you can do with this picture. For example, if you have a point here in the domain and look at its image in the target, here's a reasonable question you could ask, and by the way, we will. This is something we're going to be very interested in coming up pretty soon here. And that is, okay, maybe the domain represents location. Like here we are in a room. I could consider that corner sort of the origin. And then the value of the function, let's say temperature. Right? I think it's a nice, relatable example. You can imagine there's a different temperature everywhere in the room, all of which are too warm. Right? So, but for every point, there is a corresponding temperature. And it's probably warmer near the light bulbs and probably cooler in the dark corner down low, that sort of thing. So temperature is a function, and it varies. So here's the reasonable question. What would happen if I were to start moving in the domain, right? And so I'm right here. if I start moving in that direction, how does the temperature change? If you think about it, if my position depends on time, then the temperature will depend on time, and I could reasonably ask what is its velocity. So given what you might call an input velocity, perfectly reasonable question, what is the resulting output velocity? Now, how to answer that question is a whole conversation. We'll get to that. That's going to take us a while to build up to, right? So the answer to the question is not the point here. The point here is that this picture gives me a, I believe, very satisfying picture of the question itself. I can see my input velocity. I can see my output velocity. Thank you, literal picture. Everybody good? Okay. All right. Okay, moving along. Level sets. Again, I want to start with a concrete-ish example. Here is a function, R2 to R1, formula. We will eventually be able to talk about the graph of this function. But let's draw a different picture. Instead of setting this equal to a new variable, I'm going to take this function and I'm going to one at a time set it equal to different output values that it might in fact be equal to. So if I were to set this equal to 1, you look at this equation, x squared plus y squared equals 1. Well, that's a circle. It's the unit circle in the xy plane, and I can draw a picture of that. I could set it equal to 2. X squared plus y squared equals 2. Well, that's another circle. Still centered at the origin, a little bit bigger radius. That's something that looks like this. Okay. So these are what we call level sets. These are sets of points in the domain, all the points on any of which land on exactly the same specified output. All right, so in particular, this process, we use this notation. Here. The idea being, let me focus on. I started the wrong one. This notation here. The idea being that given an output value, from that output value, I'm asking what is the collection of all corresponding input values. And now notice what happened. This is what I started with. I specified an output value, and then I concluded a bunch of points in the domain. Notice that the action is going to the left. It's like we're going opposite of the direction of f, and thus this notation to write it as f inverse. Now, again, confession, that's an abuse, arguably, of notation. It makes it look like I'm inverting the f function. F isn't invertible. Right? This point has infinitely many pre-images. It's not invertible. I can't talk about the f inverse function. But, okay, still, this communicates the idea of the backwardsness of starting with an output and concluding points in the input. So the f inverse notation is pretty standard, pretty convenient, satisfying, even though you have to be careful not to overinterpret. Okay. Everybody okay with that? Okay. So here's the formal definition then. It's really the same thing that we've just been talking through. The idea is for a given output in the target, right? Specify that output and then ask what are all of the corresponding inputs that give rise to that output. So that's all that notation means. Okay. All right, let me show you an example. Y'all have actually seen the following example, I'll betcha. And that is this weather map right here. So this is how they used to talk about the weather. Now everybody's got the weather on their phone, and you don't need a map. Everything's tailor made for you personally. It's totally awesome. But if you don't have that, and if you're just looking at television, for example, and they're trying to describe the weather, they might draw a picture like this, and all of this kind of light brown section here, all the locations in this light brown section, the temperature is in the 50s, some 50 to 59 or whatever. And then likewise, these yellow ones are all in the 60s, and these gray ones are all in the 40s, etc. So I claim there's a level set. There's actually several level sets in this picture. Let's talk about this curve right there that I've just highlighted in black. This is where the temperature is right on the border between the 40s and the 50s. And now I ask, what temperature is it that is right on the border between the 40s and the 50s? And, well, it's 50. Right? So this curve right here is where the temperature is exactly 50. This is the curve that you get when you set the temperature function equal to 50. This, therefore, is a level set of the temperature function, right? And likewise for all of these, let's see here, all of these sort of, boundary lines between these colors. These are various different level sets of the temperature function. Does that make sense? So if you want a geometric intuition, or any sort of intuition about how to make sense out of level sets, think about how you interpret the weather, right? I mean, if you were to see this probably on your grandparents' television, right? That's where we are. And that would appear to be kind of halfway right smack in the middle of the 50s section. I think I would imagine that this is probably about 55 where we are, right, when this map was made. So there you go. You have a pre-existing geometric intuition for level sets. Okay, here's another one. Contour maps. Topographical maps, they call them sometimes. If you've ever done any hiking, you've probably seen these. So in a topographical map, a curve like so is called a contour line, and that is where you fix the altitude at a single value. So this, for example, might be where the altitude is equal to, let's say, 300, for example. And then this maybe is where the altitude is 200, and this is where the altitude is 400, et cetera, et cetera. And so you can kind of, again, sort of piece it together in your mind. Each one of these lines, as you go closer to the mountaintop here, is showing you where altitudes are increasingly high by, let's say, 100 feet per jump. So that helps you get some sense for the shape of the mountain. Now, I claim that you can use this to make decisions in certain ways. So, for example, if I were here and I wanted to get to the top of the mountain there, and if there was a trail that looks like that on the map, and if there were a trail that looks like this on the map, now I got to decide which trail do I want to take. Do I want to take the green trail or the blue trail? Maybe when I was younger I might entertain the blue one, but at this point that's looking really, really steep, right? I mean, keep in mind, each one of these lines represents 100 feet. Okay, so this blue trail, there's 100 feet of elevation gain over a very short horizontal distance. That means it's super steep. All right. That's a lot of work. Let's look at this green path. It gains about 20 feet over the first quite a nice, comfortable distance. And then, I suppose eventually it has to going up. But even at what you might call the steepest part here, it's still gaining that same 100 feet over a much greater horizontal distance. That's a much gentler, much more reasonable, pleasant hike. So now, I'm not saying you have to use the green. If you want to do the blue path, go for it. I'm just saying the topographical map here helps us see the difference between these two paths and helps us make good decisions accordingly. Okay, real quick last thing, I'm just going to point to an actual topographical map. If you've ever wondered why why roads on mountains do this zigzag thing, they're doing that because most cars can't go straight up the side of the mountain, right? And so, for example, if you were to literally do like that, well, then you're going to gain however many feet of altitude that is over that relatively short distance. Whereas if you do that instead, same altitude gain, of course, right? But you get to stretch that out over more distance, and more cars can actually, have enough oomph to be able to actually do that. So switchbacks, they call this, and you can see on the topographical map, because of level sets, you can get a sense for the motivation. Yeah.
This is super random, but is this in New Hampshire?
No. I'll bet you there's a lot of mountains that look similar. This is in Colorado. This is Mount Evans.
No, there's just a Mount Evans.
Oh, is there really? Really? Oh, wow. What are the odds? No, this is the one in Colorado. This is the highest paved road in the continental U.S. So, kind of interesting. That's a weird coincidence. See y'all later. Have a good one.